ever get the feeling like we're living in the future? I mean, AI, it's everywhere these days.
It's true. It's really remarkable.
Yeah, but today we're hitting the rewind button a bit, taking a trip back to like 1982,
Oh, wow. Okay.
before AI was the
The big thing.
the big thing. Exactly. Our deep dive today, this groundbreaking research paper by J.J. Hopfield.
Right.
This guy was onto something huge, GE, predicting the power of collective intelligence in networks way back then.
Wow.
It's like finding like a vintage blueprint for AI hidden in plain sight.
Yeah, it really makes you appreciate how these like early pioneers were already grappling with like these really complex concepts that are, still shaping the field today.
Absolutely.
Hopfield's paper, it wasn't just prescient, it was practically prophetic. Like he really saw where things were going.
Totally. Okay, so let's unpack this 1982 paper a bit.
Okay.
Hopfield, he describes this system, right? It's a network of interconnected neurons. Think of them like light switches, either on or off.
Okay, I'm with you.
Seems simple enough, right? But here's where it gets wild. He predicted that complex computations, like real, brain power stuff, could emerge from the interactions of these really simple units.
And that's the real genius of his work. He wasn't just describing a new type of computer architecture. He was really proposing a fundamentally different way of thinking about, like, intelligence itself, right? It wasn't about this complex programming. It was about the power of simple units all working together in this really elegant way.
So kind of like how a single ant might not seem all that smart on its own, but a whole colony working together, they can achieve some pretty incredible things.
Exactly. It's a power of collective intelligence. And
Yeah.
Hopfield was able to demonstrate this through these really elegant simulations, showing how these networks could actually perform these sophisticated tasks, like something called content-addressable memory.
Okay, I have to admit, content-addressable memory.
That's a mouthful, yeah.
Sounds a bit intimidating, yeah.
Yeah.
Can you break that down for me? What does that even mean?
Sure. So imagine you're searching for something online, right? But instead of having to type in the exact keyword, you can just type in like a related word or even just like a fragment of the idea. And the search engine would still know exactly what you're looking for.
Okay.
That's like the basic idea behind content-addressable memory. You can retrieve information based on like the content of the memory itself, even if you only have this partial or even like this incomplete address.
So instead of remembering something by its location, like in a file cabinet, it's about remembering based on what it is.
Precisely. Like think about remembering a song. You might not remember the title or even the artist, but if you just hum a few bars, suddenly the whole thing comes flooding back to you.
Right.
That's your brain using content-addressable memory.
Wow, that's actually really cool. And Hopfield's networks could do this.
That's right. He demonstrated how by feeding the network like a small piece of information, it could actually reconstruct this entire memory, just like completing a jigsaw puzzle, but you only have a few pieces to start with.
That's incredible. So we're not just talking about like simple storage here. The network is actually like understanding the information, right? And making these connections.
Yeah, it's like the network is able to like see the whole picture even when you only give it a few of the brushstrokes.
Okay, that's seriously blowing my mind. So how does this relate back to AI though? Like what's the connection?
Well, this ability, right, to recognize patterns, make these connections, even with incomplete information. It's essentially what, like, at the core, what we're trying to achieve with AI today, isn't it?
Oh, wow. Okay.
And Hopfield's work, what it showed was that this kind of intelligence, this really remarkable ability, it could actually emerge from these simple networks, which was, it was kind of a radical idea back then.
Yeah, totally. So it's not just about building like faster computers. It's about understanding how intelligence, how this really complex thing, how it actually works at a fundamental level.
Exactly. And what's even more amazing is that these networks, they're incredibly robust. Like even if some of the neurons malfunction or, some connections break down, the network as a whole can still function. It can still do its thing.
Wait, really? So it's like our brains, like being able to think even when we're tired or haven't had enough coffee.
You got it. It's exactly like that. This fault tolerance, it's a huge advantage, especially when you consider like how messy and unpredictable, real world data can actually be.
That's incredible. It's like the network has like a built-in safety net or something.
And that's not all. Hopfield, he also discovered that these networks, they exhibit this form of forgetting. So as you add more and more memories to the network, it eventually reaches its capacity, right?
Yeah.
And then it starts to overwrite older memories, kind of like, our own brains do.
So even the way these networks forget is similar to how our brains work. That's wild.
It is wild, isn't it? And Hopfield even proposed these ways to make the network prioritize newer memories over older ones. Like how our brains tend to prioritize more recent information. It's all about the connections and the interactions between those simple on-off units, those light switches we were talking about.
Wow. This is all incredibly cool, but I have to ask, like, where do we actually see Hopfield's ideas playing out in the real world today? Like, what's the, I don't know, the practical application of all this?
Well, think about it. His work really laid the foundation for so much of what we see in AI today.
Wow, okay.
Think about image recognition, for example. When you use your phone to identify a plant or do a reverse image search,
Right, right.
that's built on the principles that Hopfield outlined in his paper way back in 1982.
No way. So every time I take a picture of my dog and my phone just, like, knows it's a dog. That's thanks to Hopfield.
In part, yes. His work paved the way for the development of what we call associative memories. And these associate memories, they're used in everything, from natural language processing to, like, recommendation systems.
So from suggesting a new song I might like to recognizing faces in a crowd.
Exactly.
Hopfield's work is everywhere.
It really is. It's all around us. His insights, these really profound insights about collective intelligence, about content-addressable memory, about the robustness of these networks, it's had this really profound impact on the field of AI and really on our understanding of intelligence itself.
Seriously, it's mind-blowing to think that like this one paper from 1982 could spark so much innovation. We're talking about like the foundation for things that most of us use like every single day without even realizing it.
Yeah, it really highlights the importance of fundamental research, doesn't it? Like these foundational ideas, the ones that Hopfield laid out, they have this ripple effect. They end up influencing like generations of scientists and engineers.
Absolutely. But it's not just about the technology, is it? Like, we talked earlier about how Hopfield's work, it kind of challenged this traditional view of intelligence, right? What are like the bigger implications of that? Where does that lead us?
Well, I mean, if intelligence can emerge from these simple networks, like these really elegant systems that he was describing, it makes you wonder, where else might we find it? Could it exist in systems that, we haven't even considered yet?
Whoa, okay, that's a pretty big thought. So instead of always searching for like some central seat of consciousness, maybe we should be looking at how complexity itself, the way these systems interact, how that can give rise to like emergent intelligence.
Exactly. It's this paradigm shift. Hopfield's work suggests that intelligence, it isn't necessarily about having a brain exactly like ours. It's more about the way information is processed and used within a system, any system.
That opens up so many possibilities. It's like we're not just redefining what AI can do, but what intelligence itself actually means, how we even define it.
And that's what makes Hopfield's work so remarkable. You know, it wasn't just this technological breakthrough, it was a philosophical one too. It forced us to rethink all of our assumptions about intelligence, both natural and artificial.
It's a good reminder that, like, the most groundbreaking discoveries, they often have these implications far, far beyond what we can even imagine at the time.
Absolutely.
Hmm.
It speaks to the importance of curiosity, right? Of asking those fundamental questions and being open to those like unexpected answers. Who knows what incredible breakthroughs are just like waiting to be uncovered,
Yeah.
if we just keep digging deeper, keep asking those questions.
That's all the time we have for today's deep dive. We journeyed back to 1982, explored the world of Hopfield networks, and discovered how these like simple yet incredibly powerful models, they actually foreshadowed the future of AI. We've seen how collective intelligence can emerge from these simple units, learned how content addressable memory works, and even pondered like the very nature of intelligence itself. Until next time, keep those synapses firing and remember, sometimes the most profound discoveries, they're hidden in plain sight, just waiting for someone to connect the dots.